What is electromagnetic induction? Electromagnetic induction is when either electric current creates a magnetic field or a magnetic field creates an electric current. So it's when you produce a current using a field, or you using a changing field, or you produce a field using a current. So it's where current is produced by a changing field or vice versa. So it's either where you create a magnetic field because of current, or it's because of current being produced by a changing field. I should say a changing magnetic field, just to be specific. And by the way, it's usually the first one. When we think about electromagnetic induction, we're usually thinking about the first one. The second one technically also works, but we're usually just thinking about the first one. Okay? So as magnetic flux, we defined this last time in the lab, but just as a reminder, magnetic flux is the amount of electric field through a coil of wire. Okay? This other one we talked about briefly in the lab too, electromotive force. It's the name for the induced voltage in a circuit. So when you do electromagnetic induction, what you get out is electromotive force. Now you might be saying to yourself, why don't we just call it voltage? Mr. B, you said it's a voltage. It's an induced voltage. Why don't we just call it voltage? The reason we don't call it voltage is because it's not created the same way, right? Voltage is created by an imbalance of charge. You have more positives on one side and more negatives on the other, and that creates a potential difference, and that is what the voltage is. This isn't that. This isn't a separation of charge. This is a changing field that produces a current. And so because its cause is different, we need a different name for it. And the name is electromotive force. Okay, what are the three things that affect EMF induced in a wire and why? There's actually four. Don't worry about it. Just we'll add a fourth. Okay. The first thing is the rate the field changes. The rate the field changes at. I guess technically the rate at which the field changes, but it's not an English class. Second thing, so the rate at which the field changes, that's the first thing. The second thing is the amount of magnetic flux. So how much magnetic field goes through. So the rate at which the field goes through, how much field goes through. The number of coils in the loop. And a fourth one, I'm going to blame Mr. Rohrbeck on this one. He totally didn't put it on the notes, even though he doesn't teach this class and only I do. It was totally him. Yeah. The fourth thing is the size of the coils. Now that kind of affects magnetic flux in a way, but I do want to make sure to label that as a separate thing. So the 4 things, not the 3 things, are these here. Okay, so what is Faraday's law? It is this. EMF equals negative NA delta B over T. EMF is electromotive force. N is number of coils / loops. If you want to grab those 2 papers there, Indy, yeah. We're on the, yep, right there. We're on the notes part of things. So N is the number of loops. A is the area of the coil. And delta B is change in magnetic field. Oh my gosh. Just spell the word. Change in the magnetic field.
Little t just time.
Huh?
Is little t just time?
Yeah, and little t is time. Yeah, I wasn't going to do that one, but you're right. I might as well. So, the 4 things that affect the EMF. Number of coils, size of the coils, magnetic flux, rate at which it happens. So, you don't actually need to memorize the 4 things. All you have to do is look at the equation and know what they are. Like, look at the equation and be like, what 4 things? Oh, there's 4 things in the equation. Magnetic flux is the change in field. Rate of change is the time. A is the area or the size. And N is the number. So if you know the equation, which I'll give you on the test, so if you know the equation, you can figure that out without having to memorize a bunch of stuff. You're welcome. All right, cruising right along. If a voltage is induced in the wire, what also has to be produced? Any ideas? Nope, that's a good guess, though. Actually, you know what? Never mind. You are right, but that's not what I'm looking for. Yes. Current. But you know what? I'm going to add Tristan's because it's also right. Yeah, it's a current. And a magnetic field, too. If you're wondering why a magnetic field's produced, it's because it produces a current, and currents make magnetic fields. So the changing magnetic field makes a current, which makes a magnetic field. Which makes some funky things happen. Funky things. Oh, I already had that on here. Whoop. In addition to a voltage and a current, what else is changing in the field? A magnetic field. Good job, Tristan. You're just one question too early. So, what is Lenz's law and how does it work? Ready? Here's Lenz's law. Get ready for it. That's Lenz's law. Yep. Lenz was like, hey, this needs a negative sign, and he got his own law for it. So let's explain what Lenz's law says. Lenz's law says that the induced voltage, the induced current, the induced magnetic field is always in the opposite direction of the changing field. So the induced EMF slash current slash what else did I say? Oh, magnetic field is always opposite of the change. Hey, but guess what? You already knew that. Because what direction does the North Pole go? So the North Pole is making a field go in. It makes the voltage go negative. If I pull the field out, it makes the voltage go positive. If I flip it around, and so now the field is going out, I'm pushing the field out, and the voltage goes positive. Pull the field in, and the voltage goes negative. It's always opposite of what you're doing. Whatever your change is, the voltage, the current, the induced field, all that stuff is opposite. Okay, before I have you do the last three, you're going to use the book to do the last three. I want to do a demo for y'all.